So, let us start the next class. In the earlier class what we did, certain properties we have done of Laplace transform. Initially, let us go through certain examples quickly, and after that we will go through the other things. The first one is applying the change of scale property, find the linear Laplace transform of sin hyperbolic 3t. So, as you know, Laplace transform of sin hyperbolic t is 1 by s square minus 1. So, f of s. Therefore, applying the change of scale of property, I can write down Laplace transform of sin hyperbolic 3t is 1 by 3 into f of s by 3. F of sin hyperbolic 3t is nothing but sin hyperbolic a t. So, you see the advantage, once I know the sin hyperbolic t, then automatically if I wish, I can simply a will be changed 1 by a f of s by a using the formula, and we get the result. So, this is one example, and I can find out what is the value of f of s by 3, 1 by 3, 1 by s minus 3 whole square minus 1. So, immediately I can just calculate and I can obtain the result as 3 by s square minus 9. So, the result of Laplace transform of sin hyperbolic 3t is your 3 by s square minus 9. The next example is on the similar line, find the Laplace transform of cos of 5t. You know the Laplace transform of cos t is s by s square plus 1. So, that again changing the scale property, we can write down that Laplace transform of cos 5t is 1 by 5 f of s by 5, and this equals 1 by 5 into, you just replace s by 5. So, that you will obtain 1 by 5 into this, and the result will become the s by s square plus 25. Let us see the next example, Laplace transform of g t, where g t is e power t minus a whenever t is greater than a and t is less than a, the value of the function g t is equals to 0. So, we are assuming initially that Laplace transform of g t is g s. So, Laplace transform of g t will be e power minus a s into g s. So, please note this one, by second shifting property, Laplace transform of g t is e power minus a s into g s. So, now we are assuming that f t is equals to e power t say. Once f t is e power t, so Laplace transform of f t, that is Laplace transform of e power t, which is known to us, which is equals 1 by s minus 1, which is f s, where s is greater than 1. Now, we are assuming g t equals f of t minus a. Your f t is e power t, therefore, your g t will be f of t minus a over here, which is equals to e power t minus a for t greater than a and 0 for t less than a. So, if you take Laplace transform of g t, in the earlier slides we have shown that it is nothing but e power minus a s into f s, where Laplace transform of f t, that is e power t, is 1 by s minus 1. So, that the value becomes e power minus a s by s minus 1. Next takes the next example, that is f t equals cos of t minus 2 by 3 pi whenever t is greater than 2 by 3 and t is less than 2 by 3. So, just like earlier example, your f t is this. So, I have to take your one function. The function here is cos of t minus 2 by 3 into pi. So, I will take a function phi t equals cos t, whose Laplace transform is known to us, and we will take f t equals this phi of t minus 2 by 3 of phi, that is nothing but your cos of this thing will come t minus 2 by 3 of pi. Now, Laplace transform of phi t, that is Laplace transform of cos t, which is known to us, equals s by s square plus 1, which is equals to f s, and Laplace transform of f t will be here e power minus 2 by pi 2 pi by 3 into s. Here your a is 2 pi by 3. Basically, we have made t greater than a and t greater than t less than a and the value of a here is 2 pi by 3. So, that it becomes e power this particular thing, this one becomes your this particular case here your a is 2 pi by 3. So, that you will obtain Laplace transform of f t equals e power minus twice pi by 3 into f s using the second shifting property. So, whenever I am using the property, it becomes very easy for us to find out the Laplace transform of unknown functions when I know the Laplace transform of certain known functions. The next one is your this thing Laplace transform of phi t equals this, and some alternative method you can use. Quickly let us see. Laplace transform of f t, if I do not want to use the property, then I can break it into two parts, 0 to 2 pi by 3 plus 2 pi by 3 to infinity into e power minus s t. For the first part the value is 0, for the second part the function f t is cos of t minus 2 pi by 3. But here you see you have to evaluate this particular integral, this one e power minus s t cos of t minus 2 by 3 into pi, and we are substituting this t minus 2 by 3 equals pi, simply evaluation of an integral in this case, and after evaluating the integral you are coming to Laplace transform of cos t. So, you see if I know the property earlier, in that case directly by knowing Laplace transform of cos t, I can tell what will be the Laplace transform of cos this function, and I do not have to evaluate the integral. The next one is a function is given like this, sin of t minus pi by 3 and 0, which is similar to your last example. So, I am just giving the examples, so that afterwards you can just use it, you can see go through these things and quickly you can find the solution. So, without going into details, Laplace transform of sin t is your 1 by s square plus 1, and from here I can find out Laplace transform of f t is equals to e power minus pi by s into 3 pi s by 3 into f s using the second shifting property. Now, from this f s equals to 1 by s square plus 1. So, that your result is value of your Laplace transform of the function is this quantity e power minus pi s by 3 into 1 by s square plus 1. Now, come to the another property, that is Laplace transform of derivatives of f t. Let capital F t be a continuous function for all t greater than equals 0 and be of exponential order a as t approaches infinity. And if f dash t is of class A, please note f dash t is also piecewise of class A, means piecewise continuous and is of exponential order. Because if you recall class A, we defined like that, where class A will be those type of functions which are piecewise continuous and is of exponential order. So, note that f t is continuous and is of exponential order a as t approaches infinity, and the first derivative of the function f t, that is f dash t, is of class A, that is piecewise continuous and is of exponential order. Then Laplace transform of the derivative of f, that is f dash t, exists when s greater than a, and we can say that Laplace transform of f dash t, this is equals s into Laplace transform of f t minus f 0. So, please note Laplace transform of derivative of a function is equals to s into Laplace transform of f t minus f 0. Let us see the proof of this one. Now, so at first the two cases can arise. Your case 1 is your case 1. In this case, we are assuming that f dash t is continuous. We can think of two cases. It may be continuous for all t greater than equals 0, or if dash t is the piecewise continuous. So, we are considering the first function f dash t is continuous for all t greater than 0. Then Laplace transform of f dash t, this is equals, you can write down from the definition of Laplace transform 0 to infinity e power minus s t into f dash t dt, and this equals, you can break it into by parts, e power minus s t into f t will come here, f dash t will be replaced, where value of t will vary from 0 to infinity, plus s into 0 to infinity e power minus s t into f t dt. Now, this value I can write it here. The one part will be 0, the other part will be limit s t approaches infinity e power minus s t into f t, and if I integrate this one, in this case I will get for 0 it will be f 0. So, for the first part, limit s t approaches infinity e power minus s t into f t, at t equals 0, this e power s t will vanish. So, that it will become minus s 0, and this part is s into Laplace transform of this f t. Please note this thing, that whenever I am writing this, I know the f 0 has a finite value, s Laplace transform of f t, this Laplace transform of f t is known to us since it is continuous. So, let us see, we have to only check this part, limit t approaches infinity e power minus s t f t dt f t, whether this is finite or not. If the limiting value exists, then we can say that Laplace transform of f dash t exists and it will have some value. So, for this one, we know this thing, absolute modulus of f t, this is less than equals m into e power a t for all t greater than equals 0. This we are getting since effect f t is of exponential order a. In the theorem itself, we have told that f t is continuous and is of exponential order a. So, from there we are writing absolute value modulus of f t less than equals m into e power a t for all t greater than 0, and for some constants a and capital M. For some constants will come a and capital M. So, that you can write down e power minus s t into f t, modulus of this one is less than equals e power minus s t into modulus of f t. This you are getting directly. This is equals, this is less than equals, again using the earlier inequality, this we can write down less than equals e power minus s t into m into e power a t. This m into e power a t we are getting from here. So, this equals, you can write down m into e power minus s minus a into t. Now, you see this quantity m into e power minus s minus a into t, this approaches 0 as t approaches infinity. Of course, if s is greater than a, whenever s is greater than a, this term e power minus s by s minus a by into t approaches 0 as t approaches 0. Therefore, you can say that limit t approaches infinity e power minus s t into f t, this is equals to 0. From earlier one e power, you can get limit t approaches 0, this is 0 for s greater than a. So, from this term, from these two, we can conclude that from this equation we can conclude that Laplace transform of f dash t, this one exists, Laplace transform of f dash t and exists, and what will be the value of this Laplace transform of f dash t the earlier thing which we got, that is S into Laplace transform, this will be S into Laplace transform of f t minus this value, that is f 0, and the limiting value which approaches 0. So, this completes the proof whenever you are having the function f t is a continuous function, then we are showing that Laplace transform of f dash t exists and Laplace transform of f dash t, which is equals to S into Laplace transform of f t minus f 0. Now, come to the case 2, that is the second case. In case 2, what we are showing, that is, in the first case we have assumed that f dash t is continuous. Here we are saying that f dash t is piecewise continuous. So, what you can conclude from this? In this case, the given integral whatever was there, that is 0 to infinity e power minus s t into f dash t dt. This is your Laplace transform of f dash t, which I wrote earlier also. So, this Laplace transform of f dash t equals 0 to infinity e power minus s t into f dash t. Since f dash t is piecewise continuous, that means in each particular subdomain the function f dash t will be continuous. So, this integral I can break it into n number of finite sub integrals, say 0 to a 1 plus a 1 to a 2 plus a 2 to a 3, like this way, plus a n to infinity, and in each of them the function f dash t is, each of those f dash t is continuous. So, since f dash t is continuous in each of the sub intervals, therefore, just like case 1, we can prove in the similar way, in each of the sub intervals the integral exists and it has a value, and if we calculate, we will get the value as same as we got it for the case 1, that is Laplace transform of f dash t. This is equals S into Laplace transform of f t minus f 0. So, please note that once I know the Laplace transform of f t, then very easily using this theorem I can say what is the Laplace transform of derivative of that function also, which is nothing but S into Laplace transform of f t, which is again known to me, minus f 0. So, this is the Laplace transform of derivative of the function. Now, come to the this one, this we have just written like this, whatever I described. You can go through these slides and you can see it over here. You are getting it, and from here you are saying e power modulus of e power minus s t f t approaches 0. So, from 2 we are concluding this, and S Laplace transform of f dash t exists and the value is S Laplace transform of f t minus f 0. For case 2 again, f dash t is piecewise continuous. So, integral 1 may be broken as the sum of integrals in different ranges, such that f dash t is continuous in each of the subdomains, and proceeding as in case 1, we can prove the same thing. Now, let us take the next one, that is Laplace transform of nth derivative of f t. Means once I know the derivative of Laplace transform, what can be the Laplace transform of nth derivative of a function? This is equals s to the power n Laplace transform of f t minus s to the power n minus 1 f 0 minus s to the power n minus 2 f dash 0, like this way, minus f n minus 1 0. So, let us see how we can prove this thing. One thing I know, already we have proved Laplace transform of f dash t. This is equals s into Laplace transform of f t minus f 0. So, this we already know. From here, if you apply again, what will be Laplace transform of f double dash t? It should be s into Laplace transform of f t minus f dash 0, because f 0 is replaced by f dash. Here in this we have replaced f by f dash, your f dash is the function. Again Laplace transform of f t is known to us. So, we can write down s into, sorry, this will be also f dash, because f t is replaced by f dash t. So, now I know the Laplace transform of f dash t from here, that is s into Laplace transform of f t minus f 0 and minus this f dash 0 will come over here. Once f dash 0 is coming over here, so this is s square into Laplace transform of f t minus s f 0 minus f dash 0. So, whatever nth derivative we talked about, that is this one. So, Laplace transform of f double dash t, which we are showing as s square Laplace transform of f t minus s f 0 minus f dash 0. Now, whenever we try to find out Laplace transform of f triple t, that is third derivative of the function f, Laplace transform of third derivative of the function f, we can go on the similar process and we can write down Laplace transform of third derivative of f of t using the property s into Laplace transform of f double dash t minus f double dash 0. Simply we can write down, because f is replaced by f triple dash t. Now, this f double dash t you can simply write it as, again I know it, in the last one we have done s square into Laplace transform of f t minus s into f 0 minus f dash 0, using the second derivative we are getting minus f double dash 0. Now, everything is known, since Laplace transform of f t is known to us. So, we can write down s q into Laplace transform of f t minus s square into f 0 from here minus s f dash 0 minus f double dash 0. So, like this way if we proceed, in that case we can tell that Laplace transform of f n t, this will be equals to s to the power, for 3 it was s to the power 3. So, it will be s to the power n Laplace transform of f t minus, this will be s to the power 3 was there, then 2 was there. So, it will be n minus 1 into f 0 minus s n minus 2 into f dash 0. Like this way it will proceed, and ultimately the last term which you will get f n minus 1 0. Here when it was 3 you was getting f double dash 0. So, that here you will obtain f n minus 1 0. So, Laplace transform of f n t also we can find out by this way if the derivatives are known to us. So, by the derivative, whenever you are telling, when the Laplace transform of a function is known to us, I can find out what can be the Laplace transform of the first derivative of a function and second derivative of a function and nth derivative of a function also. Similarly, we can find out from here. Now, just we have shown this thing f dash t, I am showing it in some other way. So, f double dash t we have shown here, then we are showing f triple t and then Laplace transform of this one. So, this is the derivative of a function. The next one is the Laplace, you just see this thing we have written in terms of summations. S n Laplace transform of f t minus summation r equals 0 to s n minus 1 s to the power n minus 1 minus r f to the power r 0. So, r is varying from 0 to n minus 1. So, that last term this n will vanish and only this term f n minus 1 0 will be there. The next one is Laplace transform of integrals of a function. If f t is piecewise continuous and satisfies absolute value modulus of f t less than equals m into e power a t, or in other sense m f t is the exponential order a for t approaches infinity for some constants a and m. Then Laplace transform of 0 to t f x dx, this is equals 1 by s Laplace transform of f t. So, Laplace transform of integral of the function is equals to 0, integration of that function is equals to 1 by s Laplace transform of f t, or in other sense Laplace transform of 0 to t f x is equals to this quantity. So, let us see how we can give the proof. Your g t is equals to 0 to t f x dx. We are assuming, so that whenever you are writing this g 0, 0 to 0, so that the value will be 0. Now, what is your g dash t? Your g dash t is nothing but d dt of g t, and d dt of g t is this one 0 to t f x dx. So, that it will be some function of t ultimately, because it is from 0 to t. So, what is your Laplace transform of f t? Laplace transform of f t, you know it. Laplace transform of f t is Laplace transform of g dash t. F t is nothing but g dash t, we are assuming. So, this is equals, again using the earlier theorem, that is derivative, Laplace transform of derivative of a function. You can write down s into Laplace transform of g of t minus g of 0. Your g of 0 is 0 from here. So, that you are getting s into Laplace transform of g of t, or in other sense I can, from here I can tell 1 by s into f s, Laplace transform of f t, 1 by s into f s, 1 by s is coming here, and Laplace transform of f t I am assuming as f s. This is nothing but Laplace transform of g t. And what is your g t? G t is nothing but t of this thing, Laplace transform of 0 to t f x into d x. So, from here if you see Laplace transform of f t, we are getting s into Laplace transform of g t, and then we are proving that Laplace transform of 0 to t f x dx is nothing but 1 by s into f s, where f s is the Laplace transform of this one. So, therefore, if I know that Laplace transform of f t is f s, then Laplace transform of d dt of 0 to t f x dx, this is equals 1 by s into f s. So, this is the theorem on the, or in other sense, if I know the Laplace transform of a function, then I can find out what is the Laplace transform of derivative of that function also. Thank you.